Hi. So we're going to start a new chapter, and it's a doozy. It's on phase diagrams. So we're going to be moving beyond the simple phase diagrams that you see in Physics 1150, 1151, solid, liquid, gas type stuff. And we're going to be moving into phase diagrams that also consider things like the percent composition of the material, which kind of takes it up a notch. So here's the typical phase diagram that you might see in Physics 1150, 1151. So let's remind ourselves of some of the terminology and things that are going on in this phase diagram. So first of all, this is the phase diagram for water, okay? So we know that at atmospheric pressure, which is shown here at 1 atmosphere in the dashed line, at 0 degrees Celsius, water freezes, and it's a solid. Okay, and then at that 0 degree line, it'll start to melt, and eventually it will become totally water in the liquid state, and then it'll boil at about 100 degrees Celsius, depending on your altitude and the pressure, but roughly 100 degrees Celsius it'll boil, and then it'll go from a liquid to a gas. And of course, there's all these different lines on here that indicate the transition from one phase to another. Okay, so you have your liquidus line, and the liquidus line is the transition from the solid to the liquid, and so that's shown here. You have your lines indicating the transition from the liquid to the gas, and then you have here the triple point. Now remember that on the line, while you're sitting on the line, that the material can exist in both phases at once. And so what happens is, when water goes from a solid to a liquid, it takes energy to kind of heat it up, and that Q is equal to mc delta T kind of way that you learn about physics in Physics 1150. And then once it reaches 0 degrees C, it won't change temperature anymore until it's completely melted. Okay, so it holds steady at that temperature. And while it's holding steady at that temperature, it'll be in the process of melting, and you'll have both solid and liquid while it holds at that temperature. So that's kind of as represented here on the line. It's where the material can coexist in the two phases. Where all these lines intersect, that's known as the triple point. And the really fun thing about the triple point of water is, of course, it can be in all three phases at once, solid, liquid, and gas, all at the same time, which is kind of fun. So that's a little bit of a reminder of what's going on with material in these kinds of phase diagrams. Now there's another phase diagram that you might have looked at in some elementary chemistry classes or in high school or whatever. And that has to do with the percent composition of the material versus the temperature. So instead of plotting pressure versus temperature, for example, as we saw in the water phase diagram, then you can change the composition versus temperature. So this phase diagram shown here is the sugar-water phase diagram. And so as you go along the bottom of this plot, you're increasing the weight percentage of sugar in your sugar-water solution, okay? So from this, you're getting a mixture. So there could be more than one phase going on. For example, here's your solubility limit. That's the solubility limit line, that kind of arcing line on the last right-hand third of the graph. And what happens is that at a given temperature, let's pick room temperature, for example, as you add sugar, you can get the sugar to dissolve into the liquid phase up to a certain point, up to a certain weight percentage. And then past that, you're not going to be able to get the sugar to dissolve anymore. It's going to stay in its solid state just as a precipitate, for example, on the bottom of your glass or bowl or whatever. So the limit, the weight percentage limit for that is indicated by the line. And if you go across to the intersection at 20 degrees Celsius, you can see that that intersection happens at about 65 weight percent for the sugar-water solution. So what can happen is, let's say that you heat your solution up to, say, 80 or 90 degrees C. Okay, well now if you're at 80 degrees C, you can see that your limit is a higher weight percentage. Okay, so you could mix more sugar in. So let's say that you go up to 80 degrees C, you mix more sugar in, but then you cool it off. And as you cool it off, some of that sugar that you got to successfully dissolve at 80 degrees C is going to precipitate out into little crystals on the bottom of your glass. So that's kind of what's going on with that kind of phase diagram. So basically, you're in a situation where if you alter your temperature, you can change the number of phases. So for example, if you go from A to B here, you're starting at a temperature of, say, 20 degrees Celsius with 70 weight percent of sugar, and you've got two phases. You've got your liquid and your solid precipitates. And then if you go up, then you cross that line, you've heated it up, and then some of that sugar that precipitated out of the solution will dissolve in to the liquid state. Okay, so that changes the number of phases from 2 to 1. Now, if you add more sugar and you go from B to D, then you're going to go from a liquid state to a liquid and a solid state where that sugar just won't dissolve in anymore. So that's kind of what's going on there. Now, I wish I could say that all of the phase diagrams in material science were as happy smiley as that. But what happens in material science is that you get more than one kind of solid phase, and they can actually have different structures. So for example, this is an image of aluminum and copper formed in an alloy. And you can see here that it's kind of a cool looking picture actually, that there's two different phases present. One of the phases shows up as darker than the other. So the alpha phase actually has a dark color to it, and the beta phase is a lighter color. And this is, I believe, from an SEM image, a scanning electron microscope image of the two phases. Okay, so those two phases, they're both solids, but they're physically and chemically distinct regions that form, okay? So they might have different crystalline structures, and they also are different chemically. They have different chemical compositions. Perhaps one of them, for example, probably the copper, the alpha phase copper, is copper rich, and then the beta phase has more aluminum, okay? So it's a lighter density phase as well. All right, but before we embark on the really super fun, phase diagrams that you can get into in material science, let's start off with the simplest system possible so you can get used to looking at them, and so you can learn how to do some of the techniques for analysis. So the simplest thing that you can do in material science is to have a system with two components, like nickel and copper, that are completely soluble in one another. All right? Now, they both have the same crystalline structure. They're both FCC, and they have similar electronegativities and atomic radii. So you might remember the Hume-Rothery rules that we covered in a previous lecture. So these two things have very high mutual solubility. All right? So they're totally soluble in one another for all proportions, which is awesome, and as we'll see, really unusual, actually. So if you look at the copper-nickel phase diagram, what you can do is you can indicate the phases as a function of temperature, composition, and pressure. You can plot the pressure too, like we did for the water phase diagram. But for this course, those can get kind of complicated and complex. So for this course, we're just going to look at binary systems with two components, like copper-nickel, and we're going to only examine the independent variables of temperature and percent composition. And we're just going to hold the pressure at 1 atmosphere, which is what the standard kind of is for comparison anyway, since we're at 1 atmosphere here. Okay, so if we do that for copper-nickel, then this is what the phase diagram looks like. You can see the liquid portion is in green and the solid portion is in blue. And we're going to call the solid phase here the alpha phase. Okay, so this is the alpha solid phase. And it's an FCC solid solution. Along the bottom of the graph is plotted the percent change in weight percent of nickel. So you start all the way here on the left-hand side where you've got all copper, and then as you increase your weight percentage, you end up eventually on the right-hand side where you have pure nickel. Okay? Now the temperature increases here. We just zoomed in on the high temperature near the melting point for these percentages, because of course below that, below 1,000 degrees C, of course it's a solid, and above where it goes, where nickel melts, of course it's a liquid. Okay? So there you go. Now you can see if you look at this phase diagram that copper and nickel have different melting points, okay? If you're over here on the left-hand side at 0 weight percent nickel, then that's the melting point of copper, okay? And if you're over here on the right-hand side at 100% nickel, then you read it off, that's the melting point of nickel, okay? But you can see that in the intermediate region here, because the copper and the nickel do have different melting points, then you're going to get a region in between your liquidus and your solidus lines where you have a mixed phase, where you have some liquid and some alpha phase material. And this is because copper and nickel are different materials and they don't have the same melting point. So you're going to get this region where you've got a mix of liquid and solid as one catches up to the other, if that makes sense. Okay, so liquid phase, alpha phase, solid phase, liquid plus alpha phase, a mix of liquid plus solid. All right, this is called an isomorphous binary phase diagram. Okay, it's binary because it's got two components, copper and nickel. It's isomorphous because you have complete solubility of one component in the other. Okay, completely soluble means isomorphous. So this is an isomorphous binary phase diagram. Okay, so here's how to read these suckers. Rule number 1. If you know the temperature and the percent composition, then you know which phases are present. Okay, so for example, if we go to point A here, and we know that we've got 60 weight percent nickel at a temperature of 1100 degrees C, then I can figure out what phase I'm at, okay? And that phase is, of course, the FCC solid solution, the alpha phase, all right? Now, if I have a 35% nickel solution at 1250 degrees C, then I can go and I can see what my phase is. And at that point, I'm in the middle here, and I have a liquid plus an alpha phase. So it's a mix of liquid and solid there. So I can easily read these off. That's not a problem. Rule number 2, if I know the temperature and the percent composition, then I can determine the composition of each phase, okay? All right, now this is a little more complex. Let's do the easy ones first. Let's go to point A up here in the liquid region, okay? If I'm at point A, then I'm at 35 weight percent nickel, okay? So I have 35 weight percent nickel, and I have only the liquid phase present at 1320 degrees C. So my liquid is my whole phase, and it's 35 weight percent nickel. I'm done. Okay, now let's go to another easy one. Let's say I'm still at 35 weight percent nickel, but now I'm at a temperature of 1190 degrees C. That puts me down here in the solid region, okay? So I've got only solid present, it's only alpha phase, and it's 35 weight percent nickel, okay? So that's what it is. So that's pretty straightforward. But now let's go to this region B, okay, in the liquid plus alpha phase region. So I know I have alpha phase and liquid phase. Now what I'm going to do is I'm going to construct what's called a tie line. And a tie line is a horizontal, straight, flat line on this graph. It's also sometimes called an isotherm. And I'm going to look at the intersection of my tie line with my liquidus line here, which defines the boundary between the liquid and the liquid plus alpha phase, and my solidus line over here, which defines the boundary between my liquid plus alpha phase and my alpha phase. Okay, now I'm going to read off what the concentrations are at the intersection of the tie line with the liquidus line and the solidus line. And from that I can extract some information. So the concentration of my liquidus phase is, if I go over and look at the intersection with my liquidus line and I drop down and see what the concentration percentage is at that intersection point, then I see it's about 32, okay? So that means that the concentration of my liquid phase in this liquid plus alpha region at this very specific temperature is 32 weight percent nickel, okay? Now, if I go across and looked at the intersection of my tie line with my solidus line, then I can see that it intersects at a concentration of 43%, okay? What that means is that the alpha phase that's present there has a concentration of 43 weight percent nickel, okay? Now, if you think about it, this kind of makes sense, all right? So we have a phase diagram that shows us that the melting point of copper is lower than the melting point of nickel. So if you're in this region, okay, if you're in this middle region, then you know that you've probably had more copper melt than nickel, okay? So that means that the weight percentage in your liquid phase is going to be lower, right, for nickel, because it hasn't melted as much yet. And the weight percentage for my solid phase is going to be higher for nickel because nickel has a higher melting point. Does that make sense? Hopefully it does. Now, you can get even more information. Rule number 3. If you know the temperature and the percent composition, then you can determine the weight fraction of each phase, okay? So let's go back to our friend, the 35 weight percent nickel, and look at its tie line there at that temperature that we already looked at. So, so let's start with temperature A first. At temperature A, I've got 35 weight percent nickel, and I've got 100% liquid. That's pretty straightforward. At temperature D down here, I've got only solid phase, so it's 100% alpha phase, and it's 35 weight percent nickel. But now if I go back here to the middle at temperature B, then I know I've got alpha phase and my liquid phase present. I've got my tie line. My tie line intersects at 32 weight percent on one side and 43 weight percent on the other. But I'm sitting right here at 35 weight percent. So I know that I can figure out what weight percentage of liquid I have in that liquid plus alpha phase, and what weight percentage of alpha phase I have in that liquid plus alpha phase. So I can tell you not just that I have alpha phase and liquid phase, but what weight percentages those two things are. I can do that by using my tie line and what's known as the lever rule, shown here, okay? So the tie line connecting the two, also called an isotherm, what you can do is you can look at the relative weights of the liquid versus the alpha phase based on the tie line. So if you want to calculate the weight percentage of the liquid in that liquid plus alpha phase, then you look at what concentration you're at 35%, and then you compare the relative lengths of your tie line before it intersects the liquidus and solidus lines. You can compare the relative lengths of that and get a weight percentage out of it. So let's look at our tie line. If we consider R to be the distance on our tie line from the intersection of the liquidus line to the concentration that we're at, and we consider S to be the length of our tie line from the weight percentage that we're at, 35%, to the intersection with the solidus line, then I can find the weight of the liquid phase via the calculation S over R plus S, okay? S I can find by looking at the concentration at the intersection with the solidus line, C alpha, minus the concentration that I'm at, which is 35%. And then I divide that by the total length of my tie line running from the liquidus to the solidus lines, which is the concentration at that alpha phase intersection minus the concentration at the liquidus line intersection. Okay? And then I can do the same thing if I want the concentration of my alpha phase. Instead of S over R plus S, I do R over R plus S. All right? Does that make sense? Okay, so I can figure that out. Now, from this slide, it was all constructed here, breaking it down. But if I run through the calculation, for the weight of my liquidus phase, I get S, which is 43 minus 35, divided by R plus S, which is 43 minus 32, and I see that I've got 0.73 or 73% liquid, okay, at that point. And that kind of makes sense that I would have a higher percentage of liquid at that point because I'm really closer to the liquidus line than I am to the solidus line. Okay, so it makes sense that I have more liquid than solid. And of course, if I have 73% liquid, then I've got 27% solid, but if I wanted to verify that, I could just do R over R plus S, which would be, 35 minus 32 over 43 minus 32, and I would get 0.27. All right, I hope that's relatively clear. Okay, so what happens is, let's look at what happens in a vertical line. So we're holding constant at 35 weight percent nickel, and we start out in the liquid phase, and then we slowly cool it down and watch what happens. Okay, so I'm up here, I'm very far away from the liquidus line, and I'm at 35 weight percent nickel. And now I start to cool it down kind of slowly. When I reach my liquidus line, okay, then I get the formation of some little solid phase particles, okay? That's indicated in this little cartoon over here. In this cartoon, the liquid is shown in green and the solid alpha phase is shown in blue. So at B, I'm starting to see these little tiny alpha phase solid particles forming. Now, given where the thing is, okay, if I construct a tie line here and look at the intersection on either side, I've got 35 weight% nickel for my liquid phase, and then for my alpha phase, if I go across here and draw my tie line and construct to go to the other side, then I've got 46 weight% of nickel. So because my nickel has a higher melting point, the nickel is going to preferentially become a solid first, okay? It's going to preferentially become a solid first. And so these little particles are going to be very nickel rich compared to the bulk concentration of the liquid, which is 35%, okay? Now let's say that I drop down a little further. Well, if I look at what my tie line looks like here, okay, I've cooled down more. Now if I construct my tie line, my liquid phase is 32% nickel and my solid phase is 43% nickel. And as I go further and further down, I see the weight percentage of the nickel drop until when I reach the solid region, it's 35% again, okay? All right, now what does that mean really? Well, if you cool it down in an equilibrium kind of way, not much. Basically what will happen is if you do it slowly enough, your copper and nickel diffuse and move around, and you'll have a homogeneous mixture by the time you get down into the solid phase temperatures. And it'll be 35 weight% nickel no matter where you are. Okay, so that's at a very slow rate of cooling though that you get those equilibrium structures. Anytime you hear the word equilibrium in any sort of thermodynamics class, you should think slow, painfully slow. That's what equilibrium really means, okay? Things have been given time to equilibrate. Now, this is also rare because in a real manufacturing facility or any kind of thing like that, people are not that patient. They want results, they've got money, they got deadlines, and so things usually aren't at equilibrium type conditions, okay? So what happens when you're not in an equilibrium condition is that the diffusion of the copper and nickel moving around, it doesn't have time to happen, okay? And so when it starts to cool, in the very core, when the nuclei first form, you've got a very nickel-rich phase. And then as you move outward, then you're going to decrease the percentage of nickel as you move outward. So in a lot of these regions, you're going to see a nickel-rich phase on the inside, and then sort of a cord shell structure where the percentage nickel drops off as you cool it down, and as the solid phase moves away from the nucleation site. Okay. So what kinds of homework questions can possibly be asked about this? All right, here's an example problem. Is it possible to have a copper-nickel alloy that at equilibrium consists of an alpha phase of 37% nickel and also a liquid phase of 20% nickel? And if so, what temperature is that alloy at? And if not, what's the maximum percentage of nickel in the alpha phase that it's possible for a liquid phase of 20% nickel? Okay, so here we go. It's not possible, all right? I've shown you why here. I've got the diagram back up, and I've constructed a couple of tie lines for you. So the first is I constructed a tie line, a horizontal line, that intersected the solidus line at a weight percent of 37% nickel. So that's this top guy right here. So it's intersecting at about 37% nickel right there, and you can see that. So that would mean that the alpha phase would be 37% nickel. But if you go across to where it intersects the liquidus line, then you can see that the best it can do is say about 27% nickel in the liquidus phase. So you're not going to get it, okay? Now, if instead you construct a tie line that intersects the liquidus line at 20%, that's about right there, okay? Then it's going to intersect your solidus line at about 30%, okay? So the highest concentration of nickel that you'll get in your alpha phase is about 30%. So it's not possible, and instead the highest percentage that you're getting in the alpha phase is about 30% for the 20% liquidus concentration. Okay, now as you change the percentage of weight percent of nickel in this copper-nickel system, then it's going to affect various things. It's going to affect the tensile strength most dramatically, and also the ductility. Remember what we said in previous chapters about how solid solutions are affected by by the addition of these dopant atoms. So what happens is when you put in a dopant material, like let's say that you're adding nickel to copper, then those things, those atoms can act as barriers to the motion of slip and dislocations. Okay, so this dislocation can't move through once it hits that dopant atom. It acts as a barrier. And so what you're going to see is that as you increase your weight percentage for nickel, your tensile strength is going to increase. Okay, now it'll do that up to a threshold value, and it's going to depend on what materials are, what materials you're looking at, as to what the maximum is and what the composition is when that happens. But here we're peaking at about 60 weight percent nickel. What happens then is your tensile strength starts to go down. Okay, well, what's happening then is you've become, instead of a mostly copper with nickel dopants, you've become mostly nickel with copper dopants. Okay, so this is your maximum here, and now you're increasing until you really are a nickel matrix and not a copper matrix anymore. So you're going to get a peak value for your tensile strength. Okay. All right, now, of course, the ductility goes as sort of the inverse of the tensile strength. The stronger something is, the less ductile it is. We talked about that. And so you're going to see the ductility bottoming out when the tensile strength peaks. Okay? All right. I hope that's interesting. And if you have any questions, and you probably will, then please do come see me, and I'll see you in class.